Okay, now we continue to learn Chapter 3, Vector Spaces. And now we learn Section 2, Subspaces. First part, Subspace and Examples. Given a vector space V, it is often possible to form another vector space by taking a subset S of V and using the same operations of V. And the set S must be closed and the operations of addition and scalar multiplication. That means if X belongs to S and alpha be a scalar, then alpha times X also in S in this subset. And if XY belongs to S, then we know that X plus Y also in S. So we have this definition. If S is a non-empty subset of a vector space V, and S satisfies the following conditions. If X belongs to S and alpha is a scalar, then alpha X also in S. If XY belongs to S, then X plus Y also in S. Then S is said to be a subspace of V. And we know that every subspace of a vector space is a vector space in its own right. So we consider S as a whole set, then this subspace is a vector space in its own right. And 8 axioms will remain valid for the subspace, where axioms A3 and A4 follow from theorem 3.1.1 we have learned before, and the first condition of a subspace. And the remaining 6 axioms are valid for any elements of V, so are valid for elements of S. Okay. Subspaces, we consider some examples. For any vector space V, we know that the 0 set is a subspace. We call it a 0 subspace. And the whole set V also is a vector space, of course. And all other subspaces are referred to proper subspaces. For example, here we consider this subset S of R2, where S defined in this way, x1, x2. It contains a two-dimensional vector where the second component x2 equals 2 times the first component x1. So any vector in this subset must satisfy that its second component equals 2 times the first component. You can check corresponding to the addition and the scalar multiplication. Corresponding to this set S, they satisfy the closure property. Okay. And now we consider more examples. For example, in R3, if we define S, this subset equals x1, x2, x3, where the first component equals the second component, then this set is a subspace of R3. And also, if we consider CNAB, where if we write CNAB, this set contains of all functions that have a continuous nth derivative on closed interval a to b. This CNAB is a subspace of CAB. Remember that CAB contains all the continuous function on the closed interval a to b. Now we have a question. Is C1 minus 1, 1 a proper subspace of C minus 1, 1? So this C minus 1, 1 contains all the continuous function on the closed interval minus 1 to 1. And how about C1 minus 1, 1? This is a set contains all the functions which has a continuous first order derivative. So is it a proper subspace? The answer is yes, because you can find a function which is continuous on the closed interval minus 1, 1, but is not has a continuously first order derivative. Okay, so you can consider the function absolute value function. See, the absolute value function is continuous. However, at 0 point, there's no derivative, first order derivative. Okay, so this set, in fact, is really larger than this set. Okay, this is a proper subspace. And another example is that the set of all polynomials of degree less than n with a property p0 equal to 0. This is a subspace of Pn. So for this function, a functional space, vector space, you can also show that this subset is a subspace. To its own right, it is a vector space. Okay, and you can also show that the set of functions in C2AB such that the second order derivative plus the first order derivative of f with respect to x just equals 0 for any x belong to closed interval a to b. This is also a subspace of C2AB. So here, C2AB contains all the functions with its second derivative continuously. Okay, so the set of all functions here and also satisfy this equation. This is a subspace of this C2AB. You can just show its scalar multiplication and addition are closed just in this subset. Okay, and now we consider a very important subspace. We give the name null space of a matrix. Let A be an n by n matrix, and we denote by NA for the set of all solutions to the homogeneous linear system AX equals 0. So NA just contains all the solutions of this linear system. This is a homogeneous linear system AX equals 0. We claim that this null space of A, this means the solution set of the homogeneous linear system is the subspace of Rn because first the 0 vector belongs to the null space of A. So null space of A is non-empty. And also, if you check alpha times x for any scalar alpha, A times this new vector alpha times x just equals alpha times ax equals alpha times 0 equals 0. Okay, so this means alpha x also in null space of A. Okay, and we can also check for the addition. If x and y, they are vectors in the null space of A, then you can compute A times x plus y, which equals ax plus ay by the matrix multiplication, which equals 0 plus 0 equals 0. So this means x plus y, this new vector, also contains in the null space of A. So for the scalar multiplication, for the addition, those two operations are closed on the null space of A. So null space of A is a subspace of Rn. Okay, this is a null space of a matrix. This is a subspace of Rn. Now, ask you to determine the null space of A. So you can just write as a augmented matrix here. The left part is a matrix A here, and the right side is the 0 vector, because the null space just equals the solution set of the homogeneous linear system. And we use the Gauss-Jordan reduction to get its reduced row echelon form. After we get this one from the first row, you know that this refers to x1 minus x3 plus x4 equals 0. Okay, and the second row refers to x2 plus 2x3 minus x4 equals 0. So we can consider x1, x2 as basic variables, and x3, x4 we consider as free variables. Okay, we use the free variables to represent the basic variables. We can get the leading variables or basic variables. x1 equals x3 minus x4, and x2 equals minus 2x3 plus x4, and Thus, we can write x in this form. We take x3 equals alpha, and we take x4 equals beta, and we get x equals its first component x1 just equals alpha minus beta. And x2 equals minus 2 times x3, so minus 2 times alpha plus x4 equals beta, and for x3 equals alpha and x4 equals beta. Okay, so you can write arbitrary solution of this homogeneous linear system in this form, and you can divide it into summation of two vectors. See, you take those relating to alpha as 1 minus 2, 1, 0. So alpha times this vector, and plus beta times the vector corresponding to it. So it's minus 1 here, is 1 here, 0 here, and 1 here. Okay, and then you can find that any vector in this null space of A, in this subspace, can be written as, in fact, they are linear combination of these two given vectors. Okay, because alpha, beta, you can choose arbitrarily. They can be changed, right? Vector fixed here is these two vectors. So every element in this null space of A is a linear combination of given vectors 1, minus 2, 1, 0, and minus 1, 1, 0, 1.